our question working with a polyprotic acid, it asks us to calculate the pH of a 0.035 molar solution of arsenic acid. Arsenic acid is an acid that's found in our Appendix D. Even if I were unaware of the formula, I have an ability to find the formula using all of the Appendix D. Notice that the acids are just listed alphabetically. So the first thing I did was find arsenic and just read over, and I can see that it is a polyprotic acid with 3 hydrogens coming from the polyatomic ion arsenate, and I can see it has a Ka1, Ka2, and Ka3 value. With our first question, we are being asked to calculate the pH of our solution. In a polyprotic acid, it's the first ionization that contributes to the pH. So I'll begin just by showing the equilibrium. H3AsO4, hydrogen arsenate, is called arsenic acid. Letting go of its first proton to create H+, and the diprotic polyatomic ion H2AsO4 carrying a -1 charge. With that release of the first proton, the Ka1 is 5.1. Oops, let me read over. Sorry, 5.6. Repair that. 5.6 times 10 to the -3. Thinking about our ice chart, we know the initial concentration to be 0.035 molar. And of course, no ions in the initial line. The ions get made and the reactant gets used. 0.035 minus X gives us the concentration of the acid at equilibrium. When we work our Ka1 expression, we set that value, 5.6 times 10 to the -3, equal to X squared over the initial concentration 0.035. And what I'll do then is just check my 5% rule, and if I'm greater than 5%, I'll know to go back and rework for the quadratic equation. But at this time, let's just hit for the value of X, knowing that X is representing that first proton, the hydrogen ion, at equilibrium. So hitting with me, we have 5.6 E -3 cross multiplied with 0.035. We need to square root that answer to find the value of X. And when I hit, I found 0.014 molar, but I always look up and ask, thumbs up, cool, thank you. To find the pH then, we know that that's found by taking the negative log of our hydrogen. We just found 0.014. Always good business. I'll back up and check the 5% rule. If the initial concentration was 0.035, let's compare that value and see if indeed we needed the quadratic formula or was this close enough. So I'll go back and hit for my 5% rule before we find pH. Hydrogen was 0.014 divided by that initial concentration of 0.035 and expressed as a percent. Ooh, I'm finding 40%. That's way bigger than 5%, isn't it? Back to the drawing board. We'll need to go back and express 5.6 times 10 to the -3 equal X squared, but now we'll have to carry through the 0.035 minus X and work it out with the quadratic equation. 40% is not enough to disregard the X. We'll need to use the quad. All right, so let's cross multiply. Let's see, 5.6 E -3 times 0.035 gives me a value of 1.96 times 10 to the -4 minus 5.6 times 10 to the -3 X minus X squared puts my equation into the quadratic formula. So with the value of A equal to -1, the B is -5.6 times 10 to the -3, and C has a value of positive 1.96 times 10 to the -4. Let's use our quadratic formula. Plugging in A is a value of -1, -5.6 E -3 for the letter B, and C is positive 1.96 E -4. And let's reach a common answer a value of 0.01147, and I'm getting nods, perfect. So the value of X, 0.01148, I'll just round there. And remember that X was indeed equal to the hydrogen ion we found from the initial ice chart. So I'm going to go back and just record that value for X up into that data table, 0.01148 molar. So enough different from the 014 we had originally found. 0.01148 will be the hydrogen ion using the quad, and now we'll negative log that answer for pH. So I'll hit negative log of the new X value, 0.01148, and I'm finding 1.94 as the pH for that solution. The question underneath is a carried on question from the original value of arsenic acid. It's asking us to go all the way to the arsenate ion. Right now we've gone as far as 2 hydrogens, so there's 2 more removals. So I'm thinking we've got 2 more ice charts in this equilibrium. H2ASO4, what starts as a -1, removes 1 more proton to give us HASO4 -2. And thinking about the second and final ionization of that proton, we'll take off HASO4 -2, releasing the final and third proton to give us arsenate ASO4 -3. Knowing that polyprotic acid in our first problem, just the first hydrogen only, contributes to the pH, and yet we still have 2 more steps to go through to find the ultimate variable here, the concentration of arsenate with no hydrogens. When we look at this next equilibrium, it's a diprotic version of arsenic acid. This equilibrium constant we use is the Ka2 value, and in the third ionization we'll need the Ka3 value. So keeping in mind, as we remove 1 hydrogen at a time, we keep sliding over on the Ka chart as well. So the pH came from Ka1, next we'll use Ka2, and finally the Ka3. All right, here's what we know. The Ka2 has a value of 1.0 times 10 to the -7th. And while I'm staring at Appendix D, I'll also record Ka3, and that was found as 3.0 times 10 to the -12th. The hydrogen arsenate that we just found above matches the hydrogen ion we found that we used to solve for pH. The answer from our first ice chart, the value of hydrogen ion, also represented the dihydrogen arsenate. That gets carried down then as this value, 0.01148 molar. It also represents the hydrogen ion every ice chart. The 0.01148 molar that we found from our first ionization, the first ice chart, gets carried over into the second ice chart and into the third ice chart, that hydrogen ion remains constant throughout that experiment. So once I found the hydrogen, it goes down as the hydrogen in the next and into the third. So I'm going to record it there as well. The hydrogen ion found from Ka1 becomes the hydrogen ion in Ka2 and the hydrogen ion in Ka3. We'd like to know the value of X to carry over into the third ice chart. Now something fun happens with the Ka2. This expression shows 1.0 times 10 to the -7th, that was the Ka2 we looked up, set equal to the products over reactants, where the product is a hydrogen ion, 0.01148 molar, times X, the hydrogen arsenate polyatomic ion, set over 0.01148 molar, the dihydrogen acetate. In that second equilibrium, notice that these 2 values simply cancel, and the X that represented the hydrogen arsenate indeed matches the constant Ka2. And that happens every time we're working with the polyprotic acid. Ka2 represents that second concentration. So if that X, HASO4 minus 2, gets carried over into the next ice chart, that concentration of the hydrogen arsenate, 1 times 10 to the negative 7th, hydrogen ion, original value from up above 0.01148, let's solve for X. We found Ka3 to be 3.0 times 10 to the negative 12. The concentration of the hydrogen ion, 0.01148 molar. Again, the original value of X we found from the quad formula. The other ion left on top is arsenate. Set over the 1 times 10 to the negative 7th, the answer from the second ice chart, which happens to match Ka2. What we'll need to do is solve for X, where X is representing the arsenate ion with no protons left. All right, so let's hit and see if we get a common answer. 3e negative 12 cross multiplied with 1e negative 7. Divide that by 0.01148. You get a real tiny number, 2.6 times 10 to the negative 17, and we're reaching agreement. And that represents a molarity of the arsenate ion. Now friends, in practice A, it was a diprotic acid, so it only had 2 steps. This one was crazy, had a triprotic acid, so we had all 3 steps. So the number of hydrogens from that original acid determines how many ice charts we ultimately had. Alrighty. All right, let me hit end.